So today, unlike yesterday, will be more typical, because what we're going to do is we'll start off with some of the homework, and then we'll start doing new material. A little thing, I think I said this quickly, but let me reiterate. For 1.2, you don't really have to do the homework. Pretty much what you need to know from section 1.2 is, which are really hopefully easy, how to add and subtract vectors, how to multiply by a scalar, how to get a unit vector, and how to tell if two vectors are parallel. Pretty much that's it. So in the homework, they're doing some stuff with physics and so on. You don't need to know that. So if you can add and subtract vectors, if you can multiply by scalar and know what that means, if you can get a unit vector and talk about direction and whether vectors are parallel, that's good enough. So as I said yesterday quickly, again, I should really start putting these up in announcements, is for all the things there will be a review. For this week, just to try it out, because we have 100-minute lecture classes, so I want to break it up, is what I'm going to do tomorrow is I will, after half an hour, 40 minutes, share a review for a quiz, have you try it, then we'll go over the answers in class, and after class I'll put the answers up on Blackboard. And after this week, you'll then tell me if you would rather do it that way or just the more traditional way, which is Monday or Tuesday, I give you a review, give you a couple days to do it, put up answers Tuesday after class, and we go over answers on Wednesday. So for this week, I'm going to make you try it during class tomorrow. But there will always be a review for everything. Also, I think I said this yesterday, is everything eventually is on Blackboard. So if you go into course material, I have the last 3 times I've taught the class, and it has all materials from those semesters. So that will be last summer, the fall, and the spring. And so there are quizzes and quiz reviews and everything on that with answers. So you can always look if you want to compare. Last summer is probably better for comparison because I think I also did one a week, and so it should be fairly comparable. The only thing is, of course, there's no final. Okay, so let me start with 1.3, because I said 1.2 that you should be mostly ignoring. And what I do is I select a few, go over some, and then ask if you want to do any others. So number 12. So it says, given these two vectors, and I try to use some of the even ones because those answers are in the back, even though, like this one, which you'll see, aren't necessarily the best examples. Also, so I can fit everything in, I'm going to leave off most of the questions. So it's, for 12, it says, here are two vectors, find the angle between them. So first, let's do it how you really should do that when you see this, which is looking at these two vectors, what do we know about them? And how do you know? So they're parallel, and that's true because U is -2 times V, which means the angle between them is either 0 or pi. Which one is it here? And I guess the real question is, how would you know? So how do you know if the angle is going to be 0? How do you know if it's going to be pi? So in both cases, one will be a constant multiple of the other. How do you tell? It is. So I've gotten 1, 0, and a couple pi's. Right. And then this one is how you tell, which is, since it's a negative multiple, that means they're in opposite directions, which means the angle between them is pi. Whereas if it was a positive multiple, then they would be in the same direction, which means the angle would be 0. So let's pretend we couldn't do that, and let's do this the long way, which is if the angle wasn't something like nice like 0 or pi over 2 or pi, and go through the steps, which is we know that this is the definition of dot product, which means if it wasn't nice, we'd have to go through the few things. We'd have to get the dot product. So what is the dot product of these two vectors? Wait. So first, let's just do it the long way, which is the dot product is you just multiply component by component. Right, so I get negative 28. I think someone was giving me a length. What is the length of u? How do I get a length of a vector? It's just this Pythagorean theorem. Right, so I'm going to leave it as square root of 56, same thing. And the length of b is again square root of the sum of the squares, so the 9 plus the 4 plus the 1, which is square root of 14. And here, as we expected, we get this is equal to negative 1. And therefore, if I take the inverse cosine, I get the pi. If there's anything, again, except for the nice one, you can use a calculator to get it. And in theory, you should be doing this in radians, but it doesn't really matter, as long as you label. So in some ways, this problem has much of what you need from 1.2 and 1.3, which is how to take the dot product, what's the definition of the dot product, how to get a length. So any questions on this? So as I said yesterday, this pretty much doesn't have an age, so I'm going to erase now. So I'm talking so that give you a chance to see if you have any last second questions. So another one. Look at five. So the other major thing, and I'm skipping one thing which I'll talk about quickly afterwards, is I want to find the projection of one vector onto another. Here they're doing force and velocity, but we're not doing much of the physics right now, so just projection of one vector into the other one. And we know from yesterday that this is the dot product divided by the length of what we're projecting onto squared. That's all going to give me a number. That's going to be the partially the length of what we want, and then multiplied by the vector. The reason I say partially is really the direction is the vector v divided by the length of v. So one of the length of v's gives us the direction. So again, we just have the one extra piece. So here we have our definition. In this case, the dot product is -1. The length of V is square root of 2. And since we're squaring it, we then get the -1/2, and then multiplied by vector V. So that would be our vector. As I said yesterday, I don't worry about which way you present it, so you can either leave it like that, or you can multiply it out to make it -1/1/2, +1/2, comma 0. So either way. Let me be lazy. Instead of doing another problem from 1.3, let me ask, and here there's an obvious answer, but you're going to give me the short way. Are these two vectors perpendicular? And the reason this is a silly question in the context here is, if two vectors are perpendicular, the projection of one onto the other would be 0, because what we're doing when we choose projection is breaking up into the piece that's parallel plus the piece that's perpendicular. So we know they're not perpendicular, but what's the short way of checking? Right. Which is, if the dot product is anything except for 0, they're not perpendicular, or orthogonal, or normal, or whichever word you want to use. So this is typically how I do it. So I choose a couple. So these are the ones I want to look at, but any other ones that you have questions on from section 1.3. 23 or 22. Give me a second. Okay, so these are, so if you remember what I said quickly yesterday is they have things when they're doing, starting with 17 in this case, things like what's the dot product of C and 2A minus 3B? For me, looking at those, I would look at those and say, oh, well, what I would do is I would get those vectors and then take the dot product. So really any of the ones from 17 to 24, you don't need to know how to do. Since I'm not the coordinator, I don't get to decide which ones are in the homework, but we never have you do any generic things like this. So in the one level, you should be able to do it, but at the other level, you don't really have to. So for example, 23 is what's the length of A plus 5B. You can think of it two different ways. So it's saying use the fact that the length squared is equal to the dot product, so therefore it's a dot product. The length of this thing is the dot product of A plus 5B times itself, and then you can use the fact that A plus 5B dotted with itself you can distribute, but really you just don't need to know. So any of the ones from 17 to 24, and in general, any of the ones in any of the sections beyond here, such as in 1.5, and then it comes up in later sections also, these generic type questions you do not need to know. So usually I say, no, I won't do them in class, but if you really want to know, if you come to office hours, I can work with you on them. I want to emphasize that you do not need to know how to do those types. Any others? $45. Okay, so this is some ways where we started it. it says here you're given a constant force vector in newtons and a displacement vector in meters for the object. Calculate the work done if you're applying the force and you displace an object by that amount. So work. It's supposed to be a W. What is the work? How do I get the work? Right. So if you remember how we started with the dot product, which is when we talk about the work, it is the part of the force in the direction that we're moving. And that's what the dot product gives us. And then I don't worry too much about units in this class, but you'd have the joules in this case. In general, unless I say something kind of specifically otherwise, so for example, here we actually did it, you don't need to know most of the physics stuff. So they throw in physics stuff because much of this is built on top of physics, because that's where a lot of it came from. A lot of calculus started in physics with Newton. The dot product comes out of the work. The cross product will in some ways come out of another physics concept, which we'll get to. I was going to start saying it, but we haven't gotten to it yet. Any others? So we move to 1.4. Shorten it. So the question here is to find the equational line that goes through the points 1, 0, 0 and 0, negative 1, 2. So we know from yesterday that once you get past 2 dimensions, what we want to do is get the parametric equation. And the way you get that is we need a vector that's parallel to the line and a point that is on the line. So obviously, second one we have. How do we get a vector that's parallel? Right, so get the displacement vector by subtracting one from the other. What is a negative 2? Double check. Yes. There should be a negative here also. Thank you. So it doesn't matter if I subtract the first point from the second or the other way around, because all I need is a vector that's parallel, so it doesn't really matter. So I might as well get the positive numbers. I'll subtract the second point from the first. And that will give me 1, 1, 2. But negative 1, negative 1, negative 2 is fine. And then although to be consistent, should probably start with the 0, negative 1, 2, but it doesn't really matter. And there is our equation of the line. And you can either leave it like this, which is sort of the vector way of writing it, which I like just because it's shorter. I'm lazy. Or you can write it as the parametric. Which I guess is about the same thing. Little thing. On quizzes and tests, what some people do will leave off the left hand, the x, y, z equals. If you leave that off, that's not a line. Oh, so if you have a question, just type type it. So let's see. So did I just mess it up? Oh, so it's just, I should always do this, check my arithmetic. But displacement vector. So we're not adding, we're subtracting to get the two. Yes. And it doesn't matter what you call the first vector. So I did it this way just so I got positive values, but if you did it the other way, it would work just as nicely. So any questions on this? This is kind of the basic line. Okay, so let me jump to 9. So as I said, so no, so yeah, they have a second way of writing it, which Jiang is talking about here. Pretty much the only one we're going to use is the one I just erased, one of those two, the vector form or the parametric form. And Mohammed, do you have a question, or is that just because I said in this type of thing, it's easier for you to just type something in. Okay, no problem. All right, so number 9 is, in some ways you kind of guess, we're now going to do a plane. Starting with the basic one, because now for a plane, what we need is a point that's in the plane and a vector that's perpendicular or normal to the plane. So 9 is the really basic one. Here's exactly what we need. What is then the equation of the plane? So this is just reminding you what the equation of the plane is. And in some ways, it's kind of a pain to write, so let me just write it, and then you'll, as always, double check them. So that's the general one. And as I said yesterday, unless you're using it, you can leave it like that. You can also, of course, multiply it out to get it 7x minus 6y plus 2z is equal to 3 or whatever it is. So either way, in some ways, this is the form I like just because it's telling you exactly what a plane is giving us. It's saying it's all the points x, y, z that if you plug in, if you subtract the point to make a displacement vector, it's perpendicular to the normal vector. And again, like the last one, usually a couple people will leave off the thing on the right, the equal to 0. If you leave that off, then you don't have an equation anymore. So I would take off. So here, kind of going the backwards way partially. Here I want to get the equation of a line that's through the point -1, 5, 7, and parallel to the line given in the parametric form here. So here the first part is we have to get the vector. What is the vector? What is a vector that's parallel to the line? Really doesn't like my threes. So 3, -1, 9. So the idea is you should be able to read off the vector from one equation, either the line equation like this one or the plane equation like above. And then again, once you have it, it's like the other one. And so I get that. Okay, so any questions on either of these two? And in some ways that goes with this one. So here are two equations. And I want to show that these two things are parallel. And so the first thing we need to do is just for each of them. So the first thing is a line. And the second thing is a plane. And what are the two vectors that go with each? So the vector that goes with the line is, and then the vector that goes with the plane is -1, 1, 1. And the other is I should probably put the bracket so it's a vector, but it says it is. So what's the vector that goes with the plane? The normal vector. Doing my writing even worse. That's a 3, -2, and a 5. So the question is, are the line and the plane parallel? In terms of the vectors, what has to be true about these two vectors for the line and the plane to be parallel? So that so the idea is since the vector that goes with the line is parallel to a line, the vector that goes with the plane is perpendicular to the plane. For the two things to be parallel, the vectors need to be whichever word you want to use. So the question is the line and the plane parallel is the same as are these two vectors orthogonal, which means we can look at the dot product to see if it works. Just to have some name, call the vector that goes with the line L, vector that goes with the plane is the normal, and that's equal to the -3 minus the 2 plus the 5 is equal to 0. So So somewhat, yes, although in a second you're going to tell me why that isn't completely right. So the vectors are perpendicular. So why does that not necessarily tell us that the two things are parallel? Because there's one other case. What else could be true? And then it kind of depends on how you define parallel. Which is not like, so they're definitely in some sense parallel. But how could they in some sense be parallel but not really? So not the direction, because direction, remember, for parallel means they're the same. So in some ways it's kind of a weird one, which is, what would you call it if the line was actually in the plane? Would you call them parallel? And for me, I wouldn't really. So we've shown that they're sort of parallel, but it could be that the line is actually in the plane. And usually if you have two things that are the same, you don't really call them parallel. So we should sort of double check that the line actually isn't in the plane. And the way we would do that is take any point on the line and see if it's in the plane. So for example, if I put in 307, which is a point in the line, and plug it in, I get 9 plus 35 plus 4, and that certainly isn't equal to 0. And so therefore the line isn't in the plane, so therefore they're really parallel. So they're separate. So any questions on this? Oh, so what I just did was, so this part told us that they are sort of parallel, but my statement was that it's kind of a weird question if I ask you if a line is actually in a plane, whether you would those parallel. And for me, so I'm not sure this is defined exactly anywhere, but for me, I would not call those parallel. So this is showing that the line is not actually in the plane, it's separate from it, which means that they're really parallel no matter how you define it. Any other questions on this? In some ways, for people who do have little problems with this section, this is sort of the main thing, which is how you do the two things, which is one is parallel and one is perpendicular. Because we're doing this. So the line and the plane are parallel if their vectors are perpendicular. So since the two vectors are perpendicular, well, that we check by taking the dot product. So since the dot product of the two vectors is 0, that says the two vectors are perpendicular or orthogonal. And that tells us that the line and the plane are parallel. And I can't, in some ways, this is something I'd usually do on a board. So the vector n is perpendicular to the line, and the line is perpendicular to the plane. Wait, say that again, sorry. The normal n is perpendicular to the plane. The line is also perpendicular to the plane. So if you put two pencils that are perpendicular to a table, you'll see that all they have to be parallel. So if it goes the other way, if the line and the normal vector are perpendicular, then the line and the plane have to be parallel. So as I said, this is kind of the confusing thing, which you have to remember that the vector that goes with the line is parallel, the vector that goes with the plane is perpendicular. Oh, so think about it. So you have a plane, the normal is perpendicular to the plane. So put a pencil on the table. And now if I have a line that's also perpendicular to the plane, put a different pencil. Well, it's pretty obvious that those two pencils must be parallel. And we'll get that in the next one. So let me actually go to the next one because it's doing a similar thing. So we have a line. He's going through the point 75, -1, and is perpendicular to the plane given by this equation. Then give the equation of the line. So the first thing is, like the last couple, just read off what is the normal vector. And for whatever reason, they're using the same plane for all of them, so I think it's even the same normal vector as the last one. And the question is, what is the relationship between this vector, the normal vector, and the line that we want? This is the pencils thing, which is the normal vector is perpendicular to the plane. If we want a line that's also perpendicular to the plane, then it must be equal, it must be parallel to the line. And therefore, it's the vector we want to get the equation of the line, so I can just read off. That. So I said this is the little confusing part from this section, which is the relationship between the vectors and the thing, either the line or the plane. So any questions on this one? So the normal vector is by definition perpendicular to the plane. We're told that the line is perpendicular to the plane. Yeah, the +4 is telling us how high up the plane is. So if I made it +7, the vector would be the same. It's just that it might be further up or further down. So this is what we're told. What's always true, that the normal is always perpendicular to the plane. The line is also perpendicular to the plane, so I can't do it nicely here, but suppose this is the plane. And the normal vector might be here, and the line is supposed to be. And you can see they have to be parallel. It's harder to see that couldn't go some other way with this two-dimensional picture, but if you do it with pencils, it should be pretty obvious that the line and the normal vector need to be parallel. And since that's the vector we need to get the equation of the line, and is the vector we need for the line. Only in this case, because here we're told that the line is perpendicular to the plane. Obviously, in other cases, they don't have to be. So this is we're told. So this is always true. This is we're told. Because we didn't completely finish this yesterday, this section, I'm going to leave off, and I forget which ones they are, there are 2 or 3 questions where you're asked to find where a line intersects a plane. So I'm going to leave off those for now. But other ones that you want to look at from the section? Oh, so what we need to get the equation of a line is we need a point and a vector that's parallel to the line. So that's why this works. 11. Okay, so this actually partially goes into the next one. Yes. So 11 in some ways is similar to one we just did. It says here's a point. And here is a normal vector. Then get whatever you're going to get. Give a standard equation for the line in R2 or the plane in R3, which contains the point and is normal to that given vector. And the little extra thing is, if you haven't done physics, I should let you know that this I, J, and K is another way of writing vectors. I is the unit vector in the direction of the x-axis. So 1, 0, 0. J is the vector in the y direction of the y-axis, and K is sorry about the extra line, is the vector in the direction of the z-axis. So in other words, that n is the same as this. And now it's similar to the one that we did, which is we have a point, we have a vector that's normal. And plug it in. Oh, nice. Just start trying to get rid of some of these things. So in some ways, they're just writing it a different way, because in physics, this often is the way you write vectors. Any others? Okay, so in some ways, let me finish this. And I was just going to make up one, but it's probably easier to just choose one of theirs, which is, let me do the one I said skip for now, which is hopefully we'll have a nicer answer than if I just made one up. So here it's at saying, here's a line and a plane. If they do intersect, give me the point of intersection. And to do it, it's more obvious if I write the line in this form instead. So here are my two equations, or two sets of equations. How am I going to solve for that? Right. So the idea is we have 4 equations with 4 unknowns. You can either do the linear algebra with the matrix, or here it's pretty obvious that I can just plug in. So therefore, in this case, that's probably the easier way of doing it. So if I plug in x, y, and z, I get just an equation with t. So bring all the t's together. Plus 30, and this is where you really should double check them. Okay, so I get sort of my solution. I'm going to wait a second because you're going to double check to see if my arithmetic is okay. Okay, and then the actual answer will be now plug it in to actually get them. So x is equal to 3 minus that, so it's 8. Y is equal to just that number. And z is equal to 7 plus that, so something like that. And then as a double check, I could plug it into the plane to see if it actually gets 0, and it does. So if you haven't already, there's at least one more like this. You can try that for tomorrow. But otherwise, this is longer than usual. So this is kind of the usual thing, except since we did 2 new sections yesterday, a bit more homework than usual. So let's move on. So 1.5, we're doing the cross product. First, what it gives us, and then we'll actually say how to get it, so kind of go backwards. So the cross product will give us a vector with 2 properties, only one of which we will care about, although the second one we'll care about a little bit later. It's going to give us a vector that's orthogonal or perpendicular to the 2 original vectors we start with. And 2, if we form a parallelogram out of the 2 original vectors, it will give us, that's supposed to be the word area, the area of the parallelogram that we get. There's a little thing, which we don't care about, is when I say orthogonal to u and v, it is by the right-hand rule. So if you let the one finger be u and the second finger be v, then you'll get in the direction that you want. Whereas if you flip them, so if you do v cross u, you'll get the negative. Since for planes, we just want a vector that's perpendicular. We don't really care which one, so we don't worry about that too much. similar to dot product. The formula that we're going to get for the cross product, we get by using, in this case, law of sines. And so we're not going to go through it, so we're just going to pretend it is. And the way you get it is through determinants. It's not really, doesn't really have too much to do with it, but it's an easy way of memorizing how you get the cross product. So we're going to do a quick aside into the determinants. We don't care about determinants, so if you've seen them, you already know enough about them to be able to do the course. So we'll go through this quickly because, as I said, we just use it to get the cross product. I really got rid of my handwriting there. That's supposed to be A, B, C, D. So for usually at least a few people have seen it. What's the determinant of this 2 by 2 matrix? So the forward diagonal, A times D, minus the backward diagonal, B times C. We don't really care that it means something, but the determinant is used to solve systems of equations. It tells you if you're multiplying by a matrix, how much it's stretching or shifting the vectors. So it does have some kind of physical meaning, but for us, it's just a tool in the background. So let me do a quick example of just a 2 by 2, just to say what it is. I shouldn't use 3s because it always messes it up. Yes, so 3 by 3s is what we're going to use to get the cross product. So in a second, we'll say, how do we go from 2 by 2 to something larger? So we want to get the determinant of this matrix 3, 4, negative 2, 4. And you can write determinant in two ways, either determinant, or if you make the brackets around the matrix into lines, then that is notation for the determinant. So what is the determinant of this thing? As I said, that gives you an idea, if we were actually using matrices, of how much this multiplying by this matrix stretches something, but we don't care about that. So for us, it's just a tool. So what we really need is a 3 by 3. So let's look at a generic 3 by 3. And then say, how do we go from a 3 by 3, from a 2 by 2 to a 3 by 3? And the idea is it's going to be recursive. And once you get the idea for a 3 by 3, this works for any bigger one, which is, determinants are really kind of annoying, which is the way that you do them. If you have a 5 by 5, that's going to break down into a bunch of 4 by 4s. Each of the 4 by 4s is going to break down to a bunch of 3 by 3s. Each of the 3 by 3s is going to break down to a bunch of 2 by 2s. So you pretty much have to do it one level at a time. If you've actually done it, there are little simplifying things if you want. But since we're just going to use it in the one form, I'm not going to worry about any of that. And so the most basic idea of how you get a determinant of something bigger is look at the first row And in general, it doesn't really have to be the first row. It could be the first column, it could be the third row, but I'm just going to always do it the same. And so what you do is you read across the first row, take the number, get rid of, I'm not going to draw it in because it'll make my matrix really messy, but get rid of the row and the column that that number is in, and what's left, the 2 by 2, is the 2 by 2 that you get. So that's, again, it's messing up my 3's. So A22, A23, A32, A33. And as you're reading across the row, the only little thing is that the sign will alternate. So the first one is positive, second one will be negative, third one will be positive. If there were more, the next one will be negative, and then positive, and so on. Again, for this one, we have this element, get rid of the row and the column that it is in. So get rid of the first row and the second column. And again, that gets us 2 by 2. And finally, the last one, A13, get rid of the row and the column it's in, so get rid of the first row and the third column. And you get that. And now we have 2 by 2's. We now have to do each of the 2 by 2's, which I'm not going to bother with the case, but I'll do in the next page, do the actual numbers and then show how we use that to get a cross product. No, so yeah, if you know another way of getting determinants, that is fine. Usually, once you've seen it, you would use a calculator to get it, because determinants are a pain to get, but we're using it where we're going to plug in i's and j's and k's, so it's not going to work nicely with the calculator. But yeah, so if you have a different method, there's the add the extra 2 columns and then do the forward minus the backwards. If you know that, that's fine also. Yes, so plus, minus, plus, and if we start with a 7 by 7, it'd be plus, minus, plus, minus, plus, minus, plus, minus until we have all of them. So let me go to the next page. Let's do one example, actual numbers. And the reason just one is we won't do one with actual numbers again. So again, the idea is we're going to read across the first row. It's the first number. Get rid of the row and the column. Alternate. It's supposed to be a 3. Get rid of the row and the column. Alternate to plus, although this becomes a negative. It's supposed to be a line. And get rid of the row and the column. And now 2 by 2, it's the forward diagonal minus the backward diagonal. So 0 times 1 minus 2 times 1. And then same thing, 4 times 1 minus 2 times 1. And then 4 times 1 minus 0 times 1. In this case, we're going to get a single number. When we actually do it, we'll start getting vectors, but same thing. So whatever this is, 2 minus 6, so negative 8 minus 8. Something like that. As always, you're double check me. This one I'm not going to worry about because we're not going to actually do these types. Okay. So I'm delaying here just to give you a chance to tell me if I got the number right. Negative 16. As I said this way. So negative 6, negative 14, negative 16. Thank you. So let's do what we're really going to use it for, which is suppose I have u is equal to 2, 1, 1, b is equal to 3, 2, negative 1. And the way you get the cross product is in the row, this worked out nicely from one we did, is you put in the 3 unit vectors, the x, y, and z axis, the I, j, and k. And this is why it's not going to be nice to do it with a calculator, unless you have something built in. And then put in 2 vectors in that order. If you flip them, you'll get the negative value. So the cross product of u and v will be the negative of the cross product of v and u. Since we just want a vector that's normal, we're not going to worry about that, but in general, you do. And so, same as the last one, we read across the first row. So here you really do want it, even if you know a different way of doing it. So it's going to be times, get rid of the row in the column, minus j times, get rid of the row in the column. And as with the last one, give you a chance to make sure I didn't mess it up. And now they're 2 by 2, so like the last one, the forward minus the backward diagonal, so negative 1 minus 2, j times negative 2 minus 3, and then 4 minus 3. And for me, since I'm used to writing it this form, I get rid of the I, j, and k, so I get a negative 3 times I, so negative 3, 5 times j, and then 1 times k. And here, I don't have to ask you to double check because I can double check. This vector is supposed to be perpendicular to who I started with. So if I take the dot product of this with u, I get negative 6 plus 5 plus 1, which is 0. If I take the dot product of this with v, I get negative 9 plus 10 minus 1, which again is 0. So I know I've done it correctly because it is now perpendicular to the 2 vectors I started with. That's the part we really care about in this section, but in later section we'll also care that if I take the length of this one, square root of 9 plus 25 plus 1, on the area of the parallelogram that these 2 vectors form. So I is equal to, remember, is one, 0, 0, and j is 0, 0, 1, 0, and k is so they're 1 in the direction of the x, y, and z axis. So this isn't really how you have to get the cross product, but it's a way of remembering how you get it. So if you actually made these v1, u1, u2, and u3, and v1, v2, and v3, and what got it all out, we could say this is how you really get the cross product. So any questions on this before I do the next one, do how we actually use it in this section? So the reason we care, at least for now. So any questions on this? Okay. Sorry. Well, so this I is defined to be 1, 0, 0. J is defined to be 0, 1, 0. And K is 0, 0, 1. So it's always 1 in that sense. Any other questions? Okay. So so I'm just making up. It probably won't work out real nice with the numbers, but that's okay. So this is what we really want to be able to do. We know from the previous section that, or in general, that to get the equation of a line, which is a one-dimensional thing, we need 2 points. Plane is 2-dimensional, so we need 3 points to get it. If we had a 3-dimensional thing, we need 4 points, and so on, for the really basic types of things. So here we have 3 points. So that will form a plane, and we want to be able to get the equation of the plane. Just so I don't have to do it, let me give some of these names. This is the point A, this is the point B, and this is the point C. So the first thing is we can pretty easily get vectors that are parallel to the plane. So how would I get a vector that's parallel to the plane? Right, so just do a displacement vector. So for example, I can do what is the vector from A to B? And that would be 1, 1, 1. I could also get another vector from A to C. And it doesn't matter which ones I use, so I could just easily do A and B and then B and C. I just need to get 2 vectors that are parallel. Because now once I have 2 vectors that's parallel, I can use the cross product to get what I really want, which is a vector that's perpendicular, a normal vector. And as I said, we just need a normal vector, so we don't really care which order we put it in. So in terms of getting the vectors, it doesn't matter which way you did it. So if you did B to A and then B to C, or B to A and then C to A, as long as you get 2 separate ones, it's going to be okay. They're parallel to me, not to each other. That's what you're asking. In fact, if they were parallel to each other, it wouldn't work. Because if you think about it, we haven't proven it, but what the cross product gives us is the length of it will be the area of the parallelogram. So if the 2 vectors are parallel, we're going to get 0 because it doesn't have any area at all. But yes, both of them are parallel to the plane. Because if you think about it, they're actually inside the plane. And so take the cross product again, the ijk, reading across the first row, get rid of the row in the column, get rid of the row in the column, get rid of the row in the column. Sorry about that. And then the forward diagonal minus back diagonal. No, so the order doesn't matter. In general, it does if you're doing something or which way you do it, because here, when I do it in this order, I get 1, -6, 5. If I flip them, I would get -1, +6, -5. But since we just want a vector that's perpendicular, for us it doesn't matter. And yeah, so the second step, if you want to go straight from here to from the setup to the answer, that would be fine. Right. So the two vectors, we know we've done something wrong. If we do A, B, and AC and they're parallel, we would get the 0 vector. And that would be us knowing that we've done something wrong. And now we're back to the last section, which is we have a vector. This is our normal vector. We have plenty of points. It doesn't matter which one I use. So I'll use the first one. And I get that. In this setting, this is about the only one where I sometimes will actually multiply it out and bring all the constants together. Because if you do that, you can, and that's supposed to be a -6 there in the middle. If you do that, you can double check, because if I haven't done anything wrong, if I multiply everything out, if I put in the 2, 1, 1, I should get something that is true. Whereas if I've messed up, I might plug it in and get something where that's not true, something like 3 is equal to 4. And that means I've done something wrong in the middle. Any questions on this? All right, so that pretty much is 1.5. So any questions? So let me look at something. Give me a second, because I'm looking at the notes that I'm looking at, and I lost the name of the next section. So let me just look online. So. Okay. So pretty much these three sections, 1, 3, 1, 4, and 1, 5. Oh, so a little thing, yes. So I should put this in. I seem to have, in my notes, chopped off something. Is, yes, the UV sine theta. So that is the UV sine. So Danielle puts in that, why don't we use the UV sine theta for a cross product? That's sort of in the background, because that is the area of the parallelogram. So we don't really use this, but if I look at this, I get that's the length, which is the area of the parallelogram. So we could use it, but we don't really. It doesn't really come up too much. Eventually, we're going to want to get the area of surfaces, and we're going to use this fact. that really is we're using this and this, so we don't really use the middle one. So kind of in a similar with the dot product is we can use the cross product to get the angle between the vectors in some sense, but we don't need the angle for this class. And if you did the 3 by 3 with the 3 numbers, like the first example we did, we would get the area of the parallel pipette. But again, I'm not going to write that down because we don't actually use it. And similar thing, which I'm again not going to write, is that if you put in the 3 vectors, it will give you the dot product of the one vector of that with the cross product of the other 2. So a few other things, but for us, the 2 things that we use are the fact that the cross product gives us a vector that's perpendicular to the 2 that we start with, which will become useful for a couple things here and also later when we're looking for normals to surfaces. And this other piece, which is that the magnitude of the cross product will give us the area of the parallel. Those are the 2 things that we'll use later. So any other questions? So the next 3 sections, 1.6, 1.7, and 1.8, are all for us really quick ones. So similar to 1.2, really if you want, you can pretty much ignore the homework for 1.6, 1.7, and 1.8. It's in the background for some of the later things, but if something comes up that we're going to actually use, when we get to it, I will remind you and tell you what you need to know. So you really don't have to do the homework for it. You don't need it now. So it comes up as my first line says there, but the 2 underlined parts are the parts that we need. The 2 parts that we use from the cross product are, one is it gives us a vector that's perpendicular to the 2 that we started with. We use that to get the equation of the plane, and later when we're getting to derivatives, that will be useful when we're getting the equation of a tangent plane. And the second part is that the length or magnitude of the cross product will give us the area of the parallelogram. That'll help us when we want to get what's the surface area of a 2-dimensional surface in 3-dimensional space. So really those are the 2 things that we're going to be using. So if you want to use the middle thing, you can, but we don't need it. So 1.6, let's do, and then I'll stop just to show that this really is very quick. 1.7 and 1.8 are about as quick. So vector equations we've already been using, so I'm not sure why they're making this into its own little section, is things such as, well, here's one. So there's a vector equation. Here's another one, and this is how we'll start to use it later. Later we'll have to what's called parameterize things. So for example, if I call this x of t, then this is a circle of radius 2. It's the parameterization of the circle of radius 2, which in regular form would look like that. So these 2 things are sort of the same thing. The 2 things that the parameterization or vector form give us is, one, it says we're moving along So we can talk about position, we can talk about velocity along the circle. And the other, it lets us rewrite things that aren't quite functions into things that sort of are. So for example, this is not a function because if you do the vertical roll, it hits 2 points, whereas this is a function. Because for each value t that you plug in, you get 1 point. So it lets us take something that's not a function and think of it as a function if we add this extra variable. So in this one, we just have a circle. It's just there. In the parameterization form, we're moving along a circle at a particular time. And as I said, we've been using it. It's used in Calc 2 also. And therefore, for example, we know how do I take the derivative of something like this? So what is the derivative of this? Right, so just do one piece at a time. So take the derivative of the first term, which is 2 negative 2 sine of t. Take the derivative of the second term by itself, which is 2 cosine of t. That is that you should have been using this all along. But even if you had never seen this, this is pretty easy. It's pretty much the only two new things. So same type of thing. This is a vector function, so we can talk about dot products and cross products, which we'll come to. But as I said, I'll talk about that when we actually use them. So let me just do the two types that we need for now in the section that are a little bit different. Is first this thing called regular, which we'll generalize in a later section. A vector equation is regular if 1, the derivative exists, and 2, it's not the zero vector. Because if you go to the next thing, you'll see why this can be a problem. So regular just means it's nice. And in some ways, if you think about it, think about the line. If we have 2 dimensions, the derivative being 0 is similar to the slope being 0 divided by 0, which is just bad. So the other thing, not sure why I'm switching to P, but okay. And this, I'll say, be more specific when they do the actual example. Is given by this, and as often is the case, so it'll make more sense if I actually So here I have a vector equation, and I want to find the tangent line and let's make it simple, just t equals 1. So in some ways, I do almost like what you do in Calc 1, which is to get the regular tangent line, you need a point, which you get by plugging the value into the original function. and then you need a slope. It's supposed to be a 2 comma 2, which you get by plugging the number into the derivative. And then get the equation line like we usually do. Point plus the variable times it. Here, because t is usually being used inside the parametric equation for time, I'm just calling the variable something else. R, S, whatever you want to call it. If you want to use t, that's fine. It just might get confusing because we'll have 2 t's floating around that mean different things. And that's pretty much all you need from 1.6. This general idea that we have vector equations, and then how you get the tangent line if you have a vector equation. That's all you really need to know from this. So when you're looking at homework, you can ignore this 1.6. So for tomorrow, look at the homework for 1.5. And since this is as far as we've gotten for the quiz, you just need to know material up through 1.5. So really sections 1, 3, 1, 4, and 1, 5 is what you need for the quiz. And as I said, what we're going to do tomorrow, which hopefully will become more typical, unlike today, is tomorrow we will go over some of the homework, do some new material that isn't on the quiz. I'll give the review out. You'll try it in class, and then I'll put the answers up on Blackboard after class. Oh, so for example here, this one doesn't work. So if it was t squared 2t cubed, then its derivative at 0 would be 0 comma 0. And that's just kind of bad because, as I said, it's kind of similar to saying the slope is 0 divided by 0. So that's just bad. In some ways it still works, but it's not giving us what we want. And here the r, as I said, the r is just a general variable. We usually use x's and y's and t's, but we already have an x, we already have a y, we already have a t, so we're just running out of variables, so whatever you want to call it. So it's just a variable and whatever you want to call it. If you want to call it w or u or anything, it's fine. No, so pretty much we're not going to have you draw stuff in class. In particular, that's because if you have a graphing calculator, it'll do it for you. If you go into mode, you can put it into parametric mode, and it'll then ask you what is x in terms of t and y in terms of t, and it'll draw it for you. So r is a variable. So to get the actual line, we plug in all the possible values of r. So we can plug in r equals 0, and then 1 and 2 and 1.7, 2.96, and pi, and 212. And if I put in all the possible values from negative infinity to infinity, I would get the line. So r is a variable. It's just that we've already used the ones we typically use, x, y, and t, for other things, so I can't use it here. So looking forward, again, what's going to happen is I will give you a review tomorrow. I'll probably put it on Blackboard just before class, so if you want to look at it quickly, but I'll distribute also during class and then give you something like half an hour to do it. And it will be about the length of the actual quiz, so it also give you an idea what the quiz will look like. And then Thursday, the plan is first half hour is new material, stuff that is not on the quiz. I'll then stop for 15 minutes or something. I'll stay on this, so if you have questions leading up to it, and then I'll have the quiz available starting at something like 2:15. And the only little thing is, if you can't take it at this time, for whatever reason, you're going to either put something in the discussion or send me an email. And for the first quiz, I'll probably do it through Blackboard, where I'll put up an assignment. It'll be available starting at 2:15 or so, and then you'll have until 3:10. And what I did last semester is, in theory, what you'll be able to do is, when it's an assignment, you'll open up, and it's just going to be a PDF with all the questions, and you can either download that and write on the download, which is what I'm doing here, or you can print it out and write on it and scan it in, or you can just take a regular piece of paper, write on it, and then take a picture or scan it in. So whichever of those is. It makes it a lot easier if you can do it as a PDF, because it's easier if you all have the same format. But if not, it's not a huge deal. It sort of is. It's kind of a real pain. But as long as there aren't too many of you, that's not that big a deal. And if there are problems uploading it onto Blackboard, you can always send me an email with it as an attachment. Yeah, in some ways, that's what if you think about it, that's what I'm sort of doing now, which is the quiz itself. I usually try to make it take 20 to 30 minutes. But here, you can start it at 2:15, and then you have until 3:10. So you have almost an hour. So even if you have problems uploading it, it shouldn't be a problem. So I can do tomorrow. So let me stop recording, and as with yesterday, if you still have questions,